Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about confidence intervals. If you have ever read a scientific research paper involving data, chances are that it used confidence intervals to report its results. When we estimate quantities of interest from limited data, there is inherent uncertainty in our estimates due to the limited data. Confidence intervals allow us to quantify this uncertainty rigorously under certain assumptions. In this video, we're going to define confidence intervals, explain how to build them, and also how to interpret them. Let's get to it. We're going to talk about confidence intervals, and the plan is to first define them, then show how to build them for the population mean, and then finally to discuss how to interpret them. The motivation here is that we want to estimate population parameters that describe a population so large that we cannot measure every single individual. An example would be we want to estimate the average weight of a rat in New York, of the rats in New York, but we cannot catch every rat. We can only perhaps catch a subset and try to estimate our population parameter of interest from that subset. It turns out that a very simple but surprisingly effective strategy is to obtain this subset by randomly selecting individuals completely uniformly at random from the population. So just to illustrate this idea further, let's take a look at an example. Here we have a population of people, it's about 4,000 people. This is going to be our ground truth population that we're going to use as an example, which we would not know in practice. Okay, here is the histogram of these 4,000 people. Unfortunately, we cannot measure each of them. Instead, we pick a random subset of 400 people. So this is the data that we're actually seeing. We want to estimate the population mean of the height, which is 175.6 centimeters, but we don't have access to that. We want to estimate it. What we do is we average the available data, and this is the estimate that we get. In this case, the estimate is very close, 175.5. The important thing to realize is that if I repeat this process and I randomly select 400 other individuals, then my estimate is going to change. Here it has changed to 175.2 because this histogram of samples has changed, right? Because I'm selecting 400 other people. If I select 400 other people, so if I repeat my measurements again, my estimate is going to change. This is exactly what I meant when I said that there is inherent uncertainty in estimates obtained from limited data. There would be no uncertainty if I managed to measure the whole population, but that is not possible. I have to measure just a subset, and because of that, we get this uncertainty. In order to visualize this maybe a little bit better, this is what happens if we repeat the measurement process 10,000 times and we plot a histogram of our estimates. The estimates are thankfully close to the population parameter that we want to estimate, but there is uncertainty, right? You can see here that we're not exactly at the population parameter. Our goal with confidence intervals is to quantify this uncertainty, but from the available data. We need to quantify this uncertainty from the 400 samples that we obtain. We cannot do this procedure here where we sample 400 samples over and over and over and build this distribution. That is not going to be possible, because if we could do that, then we would just go ahead and compute the exact population mean. I hope that is clear. We want to quantify uncertainty from the available data. The idea of a confidence interval is to, instead of reporting just our single estimate, to report a range of values that we are sure is going to contain the parameter of interest with a certain high probability, which is typically 95%. So instead of saying our estimate for the population mean is 175, we say the population mean is going to be within the interval 174 to 176 with 0.95 probability, or 95% of the time. We will talk more in detail about how to actually interpret these statements at the end of the video. But before, we're going to see how to actually build these confidence intervals for a population mean. Okay, here we denote the population mean by mu pop and the population variance by sigma squared pop. So now we assume that we have random samples selected independently at random with replacement from the whole population, which means that each of these guys corresponds to the height of, in our example, to the height of an individual that is selected completely at random, we have the same chance of selecting every individual, and every time we take a measurement, we take it independently. We then compute our estimate, which is the average of these heights in our example, and in general, it's the sample mean, the arithmetic average of these random variables that represent the measurements. And we have seen previously, in previous videos, is that by linearity of expectation, the mean of this average is actually the population mean. The estimator is unbiased. And what we have also seen is that the standard error of the estimator, which is just its standard deviation around that population mean, decreases with square root of n. Okay, this is critical to establish the law of large numbers. Beyond the law of large numbers, we also saw that the distribution of the sample mean around this population mean is well approximated by a Gaussian with that mean and standard deviation equal to the standard error. This approximation is inspired by the central limit theorem, but we already saw empirically that it's actually really good, often even with a small number of measurements. And now the idea is, can we exploit all of this information that we have about the sample mean to build confidence intervals? So what we said is that the sample mean is centered at the population mean, and that the standard deviation of its distribution is equal to the population standard deviation divided by square root of n. So it's easy to build an interval, and we will see exactly how to do it in a moment, that contains the sample mean with a certain probability. Okay, so this, what I'm drawing here, just to be clear, is the distribution of the sample mean that corresponds to the assumptions that I just mentioned. Okay, so we're saying that if now I sample, let's say 400 individuals, and I compute their sample mean, it's going to end up somewhere here or here, and we know that it's going to be here with probability 0.95. So is this the confidence interval that we are after? Let's take a look at what this statement that I just made actually is a little bit more rigorously. So I'm saying that the sample mean is going to be in this interval, and we will worry later on about how we actually compute the width of the interval. But I hope it's clear that if the sample mean is Gaussian, centered at the population mean, we can establish an interval, if we know the standard deviation, we can establish an interval which is going to contain it with probability 0.95 or whatever probability we desire. Is this a confidence interval? Well, not really, right? Because first of all, we're constructing this confidence interval based on the population mean, which is exactly what we want to estimate. So if I had the population mean, then what are we doing here, right? Like, why are we even building confidence intervals? So this doesn't really work. But if you look at this for a moment, you realize that the fact that the sample mean is between the population mean minus c and the population mean plus c basically means that the population mean is between m minus c and m plus c. Okay, hopefully that's clear. Just, to give you a little taste of the logic, if this is true, then we can move, if this is true, then we can move the c to the other side, and this is true, right? Okay, like the population mean is greater than m minus c. So now we have a confidence interval that actually depends on the sample mean, which is what we're computing from the data. So as long as I am able to know what c should be equal to, and we will get to that point in a moment, but for now let's assume that I know what c is, I know the width of this interval around the population mean, even if I don't know the population mean. If I know that, then I can actually build an interval that is going to contain the population mean with probability 0.95, because if this happens with probability 0.95, this is completely equivalent. Okay? So we have achieved actually what we wanted. Let me draw a picture. So what we're saying is, look, if I sample a population mean, let's say here, okay? If we know that, if I sample, I said that if I sample a population mean, if I obtain a sample mean, okay, from n measurements, and it's there, we know that it lands within that interval with probability 0.95. But that immediately implies that if I take this interval and I shift it to be centered at the sample mean, which is what I know, I don't know the population mean, this line is not very straight, but I hope you forgive me for that, then the cool thing is that we are guaranteed that the population mean is actually within this interval with probability 0.95. This is the logic that I was applying. So now every time that we obtain a sample mean, as long as we know the width, and we will come back to that, as long as we know the width, then I can build a confidence interval around the sample mean with that width. Okay, so here I'm showing you different confidence intervals obtained from different sample means by essentially shifting this guy. Okay, you might say, okay, but Carlos, it's quite obvious that this guy and this guy, the first two have different widths. So what is going on here? I will explain that in a moment. But for now, just imagine that what we're doing is we're estimating a sample mean. We can somehow estimate this width. And what we're doing is we're building an interval by centering it at the sample mean, because by the logic we just explained, it will contain the population mean with probability 0.95. Okay, so now let's worry about how to estimate this width. What we're going to use is that if we have a Gaussian random variable with mean mu and variance sigma squared, then if we multiply a by a constant and we add another constant, then that random variable stays Gaussian, but now the mean has been multiplied by the scaling factor, and the additive constant has to be added to it, and the variance has been scaled by the square of the scaling factor. Okay, we're going to use this fact about Gaussian random variables to actually determine how we find the width of this interval. Okay, so now we're going to build a confidence interval for the mean of a Gaussian that has that mean and variance sigma squared. Okay, and then we'll apply this to the population mean. So the interval is going to be centered at whatever value of the random variable is, and it's going to have a width that depends on the variance of the Gaussian, which makes a lot of sense because the variance tells us how fat or thin the distribution is. And there's going to be this constant that is determined by 1 minus alpha, which is the probability that the population mean ends up in that, it belongs to that interval. Not ends up, right? The population mean is a fixed parameter. It's the interval that is random. And that is why, and this is very important, I'm putting a squiggly line on the interval, because you have to realize that what's random is the interval. As you saw in the previous picture where we had different confidence intervals every time we sample. That is very important to understand. Okay, so now let's go back here. We want to find a confidence interval for a Gaussian that has this mean mu. So now we're going to see how to choose C of alpha so that indeed the population mean is within this random interval with probability 1 minus alpha. So what's the probability that under what conditions is this not true? Well, if A minus C alpha sigma is greater than mu, or A plus C alpha sigma is smaller than mu, then we're out of the interval. So what we do is we say, okay, the probability that we're in the interval is 1 minus these two events that are disjoint, so the probability of their union is equal to the sum of their probabilities. Okay, and now what we're going to do is we're going to move things around to basically write these probabilities in terms of a standard Gaussian that has zero mean and unit standard deviation or unit variance. So we basically move things around. We move this guy here, and then we divide by sigma, and we get this expression for the probabilities. And now, if this guy is Gaussian with mean mu and variance sigma squared, then this is its standardized version that has zero mean and unit variance or unit standard deviation. So now we can express this in terms of a standard Gaussian random variable that has zero mean and unit variance. By symmetry of the standard of the Gaussian distribution around its mean, this is just 1 minus 2 times the probability that z being the standard Gaussian random variable is C alpha away from 0, and that probability we can just compute. traditionally using tables. Now you can just, use your computer. So basically this is how we obtain this C alpha. It's the probability that a Gaussian random variable, basically, okay, I made this a little bit maybe more complicated than it should be, but it's the value that if we plug it into the Gaussian CDF ensures that this standard random variable is within the interval that we wanted with probability 0.95. Hopefully that makes sense. Now, for example, if we want, 1 minus alpha, obviously. If we replace 1 minus alpha by 0.95, which was what was in my mind, now we can easily get that constant by looking up what's the corresponding probability of a standard Gaussian random variable. And the value that is used by far most commonly in the literature is 1.96 because it corresponds to a probability of 0.95. Okay, so all of this to say that if we know the variance of the Gaussian, we can basically compute that constant if we know what is the distribution of a Gaussian with zero mean and unit variance, because when we scale a Gaussian and sum a constant, then we also get a Gaussian distribution. Okay, hopefully that makes sense. I felt that was a little bit long-winded, but the point is that we can get this interval as long as we know the standard deviation of our estimator. So now let's go back to the population mean. If we have these n random samples, we want to estimate the population mean, this is the population variance, and we compute the sample mean, then we know that the sample mean is centered at mu pop. We know that its standard deviation is the population standard deviation is divided by square root of n. So now we can apply our result about Gaussian random variables, assuming that the distribution of the sample mean is Gaussian with that mean and that standard deviation, which holds asymptotically by the central limit theorem. And we have seen in previous videos that it typically holds also very well for finite n. Okay, so here we have plugged in this constant that we know how to compute because of the previous slide and the standard deviation of the Gaussian. Okay, so we have a confidence interval and this is a 0.95 confidence interval. Are we happy with this? You might not be happy with this because realize that the confidence interval actually depends on a population parameter that we will typically not know. Okay, so wait a minute. We don't know the population standard deviation. So what do we do about this? Well, we're pragmatic, and what we do is we use the sample standard deviation of the sample and then divide it by square root of n as indicated in the formula, or we can use an upper bound, which is what we will do for when we're building confidence intervals for probabilities and proportions, and as we will see in the following video. Okay, but for now, a standard approach to do this is we use the sample standard deviation, which we know is a consistent estimator of the population standard deviation and is typically going to give a reasonable estimate. Okay, so again, what is our logic? We are relying on this assumption that here again, the population is 4,000 for our example that we're using all over the place for these heights. We want to estimate this population mean. There's this population standard deviation, but we only get 20 samples. So what do? We assume that the estimator is Gaussian around this population mean, and then by that assumption, we can take the sample mean and put a confidence interval that approximates this interval, but centered at the sample mean. And what we do is we take our 20 samples, we take the sample standard deviation, and then we divide it by square root of n, because remember that in order to get the standard error from the standard deviation, we have to divide by square root of n. That's how we build these intervals. And that's why some of them have different lengths. In this case, we only have 20 measurements, so the estimate of the standard deviation is not super stable. Okay. Now I want you to think about what happens if we suddenly increase 20 to be 100. How are these confidence intervals going to be affected? In particular, is the probability that they contain the population mean going to be affected? The answer is no, right? Because that is determined by this. And I forgot to say something quite important, is that here I'm indicating which ones contain the population mean, which are drawn in a solid line and which ones don't. So from time to time, with probability 0.05 or 5% of the time, the confidence interval is not going to contain the population mean, and that's okay. This is exactly how we're constructing them. And it can happen, right? You can get very, very unlucky and suddenly just sample really tall people, as was the case here, or very short people. And then in these rare cases, the population mean is not going to be contained within the confidence interval. Okay, but back to my question, what is going to happen if we increase n to be equal 100? Well, we know that by the standard error, the expression for the standard error for the sample mean, we know that it decreases with square root of n, right? So then we know that this is going to be narrower, and when we estimate it and put it centered at the sample mean, we're going to obtain a narrower confidence interval. That makes a lot of sense. We have less uncertainty about our estimate as n grows. But the probability that the confidence interval actually contains the population mean does not change because we're fixing it to be 0.95. Okay, hopefully that makes sense. In this case, here we got unlucky and we sampled some pretty short people, but otherwise all the confidence intervals contain the population parameter. Okay, and you can see that they are narrower because the standard error decreases with square root of n and we're using more data. Okay, so now let's take a step back and see how we should interpret confidence intervals. When we have a specific confidence interval, so here we have sampled maybe 400 people from this population, and we say that the 0.95 confidence interval for the population mean goes from this value to this value. There's kind of like a strong temptation to say, well, that means that the probability that the mean height, the population mean height, is between these values is 0.95, because this guy is a 0.95 confidence interval. That kind of, if you don't think too much about it, that feels reasonable, until you realize that in our whole reasoning, we have modeled the mean height to be a constant mu pop. So in this statement, there are no random quantities. Essentially, what we're saying, and to make it really, to drive the point home, remember that in our case, the mean height is 175.6. It's this value. So what we're actually saying is the probability that the number 175.6 is between 174.6 and 177.4 is 0.95. That is complete nonsense, right? That number happens to be between those two values always, with probability 1 if you want, but basically always. So this makes no sense. Instead, how should we interpret this statement that a 0.95 confidence interval for the population mean is this? The way we should interpret it is that if we were to repeat our measurement process over and over and over and over, 95% of the time, the interval would contain the population mean. Said otherwise, when you read scientific articles, you are going to come across confidence intervals. Well, 95% of those confidence intervals contain the actual parameter, 5% of those do not. Okay, that's another way of seeing it. Because for each of them, 0.95, with probability 0.95, the parameter is in the interval. So when you aggregate a lot of such confidence intervals, 5% of them are not going to contain the parameter. That's what we're saying, and we can live with that. Just to, again, belabor this point, maybe this is a repetition in our case, which we usually, in practice, we cannot repeat this over and over and over, and we can definitely not check whether the confidence intervals contain the actual parameter, because, again, the whole point is estimating this parameter from the data that we have, right? But if we could, we would see something like this, where 95% of the time we're fine, the interval contains the population parameter of interest, which is indicated by this line. I hope that was clear. I should have said this at the beginning. Yeah, this was kind of an important detail, right? That dashed line corresponds to the population mean. Yeah, I'm a little bit sleep deprived, so these things happen. But, and from time to time, we're going to get unlucky 5% of the time, and the confidence interval is not going to contain the population parameter. Again, this also reminds us that we are modeling the population parameter as being fixed, this fixed deterministic constant, and what is random are the confidence intervals, and they are random because of our measurement process, which is randomized, right? We're selecting individuals at random from the population. Same thing for n equals 100. Again, the confidence intervals are narrower, which is really nice because they allow us to measure the uncertainty corresponding to specific values of the number of measurements. And this could inform, for example, the choice of number of measurements depending on what we want from our estimated parameter. All right, so what have we learned? We have defined confidence intervals. We have shown how to build confidence intervals for the population mean, and we have explained how to interpret them. And that's all I have. Thank you very much.